Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using Knime. In this chapter we're going to look at how to create and score and understand a decision tree. Decision trees are one of the most popular data mining techniques, and they're one of the most powerful as well because they work for both classification and prediction. The attractiveness, what makes people love decision trees, is largely due to the fact that the trees represent rules which can be expressed in English, so that, in other words, a human being can understand them. You understand why the model chose to say, I'm going to win this sale or lose this sale, as an example. Because they combine both data exploration and modeling, they're a really good, powerful first step for you to learn when building the final model, perhaps using some other technique. But it's a good way to get to learn the data as you begin. All right, well, what is a decision tree? It's a structure that can be used to divide up large collections of records into successively smaller sets by applying a sequence of decision rules. So within each successive division, the resulting sets become more and more similar to one another. And the familiar division of living things into kingdoms, phyla, classes, orders, families, genera, and species, and so on, invented by the Swedish scientist Carl Linnaeus, is a good example of one. But here's perhaps an even better one. A decision tree here based on a bachelor dropping food on the floor. The first decision point: did a boss, lover, or parent see you do it? If the answer is no, eat it. If the answer is yes, was it expensive? If the answer is yes, can I cut off the part that touched the floor? Yes, eat it. No, your call. If it was not expensive, is it bacon? Yes, eat it. No, don't eat it. This is a simple example of a decision tree, and it has created a set of rules to decide whether someone should eat food that has been on the floor. Or it could also be used as a classification. So instead of predicting whether someone will eat the food or not, it can be used to classify the characterization of how they dropped it and who witnessed it, etc., as is this edible or not? So as I said, the decision tree is just a set of rules for diverging a large heterogeneous population into smaller, more homogeneous groups with respect to particular target variable. The target variable is usually categorical. It can be, and you'll see we have a decision tree where it can be, a regression decision tree can be used as well. But it's usually a categorical variable, a yes-no flag, a 1-0, true, false, that type of thing. And the idea is that a given record belongs to these categories or classification, classifying each record as this is the most likely class it belongs to. Now, anyone familiar with the game 20 Questions will have no difficulty in understanding how a decision tree classifies records. A person thinks of a particular person, place, or thing that would be known or recognized by all of the participants. But the player gives no clue to its identity, so it can literally be a person, place, or thing. The other players try and discover what it is by asking a series of yes-no questions. The game of 20 Questions illustrates the process for using a decision tree for appending a score or class to a record. A record enters the tree at the root node. The root node applies a test to determine which child node the record will encounter next. There are different algorithms for choosing the initial test, but the goal is always the same. The goal is to choose a test that will best discriminate among the target classes. This process is then repeated until the record arrives at a leaf node. All of the records that end up in a given leaf are classified the same way. And there's a unique path for each from the root to each leaf node, and that path is an expression of a rule that's used to classify the records. Now, just like the game 20 questions, you have to stop at 20. 20 is the stopping criteria. You can't ask more than 20 questions. But anywhere along the way, you could choose to stop and say, I'm going to make my guess now. Based on the information I have, I think I know enough to make my guess. That would be the stopping criteria. What you've been doing is you've been asking questions that expressly divide the groups as much as possible with each layer of from the root all the way down to the leaf. The stopping point is going to be, look, all instances of the training set belong to a single value of y, or a maximum tree depth has been reached. Like in the case of 20 questions, you've got to 20. You can't ask any more questions than that. Or the number of cases in the terminal node is less than the minimum number of cases for a parent node. Or if the node were to split, the number of cases in one or more of those child nodes would be less than the minimum number of cases that you allow for a child node. Or another stopping and final criteria would be the best splitting criteria is not greater than a certain threshold, meaning I can't filter way more than a certain percentage of these rows. Now, much like you saw when we did dimensional reduction, we couldn't just choose a missing value threshold and just use it. So identifying the stopping criteria is one of trial and error. We'll actually build some workflows that will show you how to estimate where do we want to stop and what kind of stopping criteria we want to use by measuring the model's accuracy. So decision trees is still a fairly generic term. There are multiple decision tree inducers, and you're going to have to choose the different types that you can work with. So the most popular one, at least for right now, is C4.5, and it uses a gain ratio for splitting criteria, meaning that the splitting ceases when the number of instances to be split is below a certain threshold. There is a C5.0 that solves some technical issues with the C4.5, but it's not widely available. There's also CART. It stands for Classification and Regression Trees. And it's characterized by the fact that it constructs binary trees, meaning every node has two childs. With C4.5, I can have as many, the root node could have, 20 leaf nodes or non-leaf nodes. Anything you want goes, but CART would typically be binary. Two other common decision tree inducers are CHAID, which is a chi-square automatic interaction detection. It was designed to handle nominal attributes. For each input attribute, CHAID finds the pair of values that are least significantly different with respect to the target attribute, and that difference is measured as a p-value from a statistical test. Quest also was the quick, unbiased, efficient statistical tree. The algorithm supports univariate and linear combination splits, and then for each split, the association between the input attribute and the target attribute is computing using ANOVA. And so all of these, or a Pearson's chi-square. Hopefully all of these tests are familiar to you because we've covered all this in the statistics portion of the class. All right, before we start building up a Knime workflow to do a decision tree, let's come over here into the node repository and look for that word. I'm going to zoom in on the decision tree, and I'm going to start to minimize a few of these, and let's talk about some of the options that are available to us. We have decision trees, and we have decision tree ensemble, which is also called a random forest. We'll be covering the random forest in the next chapter. So for now, let's talk about the decision tree and the attributes that are available to us. We have a learner and a predictor, and we can take the decision tree and put it out onto an image, literally a graphical image that we want to keep. We can convert the decision tree to a rule set so that you could actually use it inside of code if you wanted to. And we also have a simple regression tree. And this is going to be used basically when, instead of trying to compute a classification, if we were trying to predict something like, say, how much revenue a customer might bring in. I'm going to want to do something with a regression instead, and it can still be done with a tree, and we'll look at that a little later in this chapter. So for now, let's just focus on the idea of the decision tree learner and the decision tree predictor. All right, so I've gone ahead and set up just the basic core here of a decision tree. And let's start by looking at the data that I'm working with. It's got a sample CSV file. And if I look at the column specifications, you can see I've got 78,000 rows in here and 19 columns. And I look at the column specifications. The key column that I'm trying to look for is the opportunity result. That has values of won and loss. And that's what I'm going to be trying to predict. And since I've got a historical data set here, I'm going to be able to use that to develop my model. But I've also got information about the sale, the elapsed time in days that it was running, the client size, competitor types, and a number of other fields. This is a standard data set that's very useful, and we're going to use it for all of our classification models so we can compare our results. And I'm going to do the same partitioning for each example. In this case, I'm going to do partitioning to say I want 70% of the data drawn randomly to go into the learner, and then I'm going to want the remainder of that data, so 70% is 54,617. The other 23,000 will go into the testing data set. So let's go ahead now and take a look at the decision tree and see all of the different variables we have to set up here just to begin with. Now, this is going to take a while because there are a lot of settings here, but let me see if I can just kind of cover the major ones right out of the gate for you. The first thing we need to know is, what is the classification column? What is, in our case, opportunity result? That's what I'm trying to get to. The next, the quality measure. The quality measure is a mathematical summary of entropy, which is the amount of how similar the data set is to itself. In my case, the quality measure, Gini index, what this is really better, I really wish they'd do it this way instead, is to say the Gini index is a CART decision tree, C-A-R-T, and a gain ratio is the C4.5 decision tree inducer. So that's really, it would be ideal to me if they put it this way instead of explaining it. Now, pruning, we have two methods of pruning, and both are useful and you can try each one. The MLD training mechanism is, or excuse me, the MLD pruning mechanism. All of this is about overfitting. So the MLD is the memory description, excuse me, the minimum description length of the pruning method. It's basically how big is your tree. If you were to set this to MLD, it would set a threshold. And within that threshold, it would try to remove rows that make the tree too complex. And if removing those branches off the tree don't hurt the score, it would go ahead and remove them. It's basically, both of these are mechanisms for, like I said, stopping overfitting. The next is reducing error pruning. It's basically looking for low populated branches, and then it prunes the branch if it doesn't decrease the accuracy of the model. So I generally leave this on, and I don't turn on MLD pruning. Now, a minimum number of records, I don't want branches that have only one record. That's in my mind clearly going down the path of having too much memorizing the data versus a clear overfit. And this number of threads is really just taking advantage of your multi-core processing capability on your computer. And the skipping nominal columns without domain information. So in other words, if the column is a nominal column but there are too many values like first name or last name, skip them. Don't bother trying to use them. Now, the last part here, force a split column. If you know more about the data than it's able to determine mathematically, you can check this and force the root split to be on something. Maybe you know something about the data, like these are internal customers and external customers, and you want the split to be that way. You can force it to actually occur this way. Also, I've never had really much occasion to use this, but binary nominal splits, if you have a nominal data type and you want it to split on binary values, you can do so to say, in other words, just if then. So if you were looking at something like marital status, you could say start by splitting single. So you're either single or you're not. And then married, you're either married or you're not. And then widowed, you're widowed or you're not, or divorced, divorced and not, and so on. So each split would only occur into two paths. Then there are some advanced additional settings in the PMML. PMML is a model format that Knime is going to support that will allow you to create a model and export it to use it in other places and on other tools. But one of the most two here is, I'm going to bring this up here on the node description because this will really help here. The no true child strategy and the missing strategy over here on the side. I wanted to bring this up here for you. So I can come back here and say the no true child strategy. If scoring reaches a node at which its attribute value is unknown, what do you want to do? So basically this is how to handle this part of the missing value strategy. I can either return a null prediction, or I can return the last prediction, which would be return the majority class of the last node. So meaning go up one node and say, what are the majority of them? What did I predict for them? I'm going to predict that for this person. And then the missing value strategy. If there are missing values in the data that have to be predicted, how do I want to handle them? Use the last known class will be the last prediction, or the default child. Use the default child and continue transversing the path. That option is not available on the screen, by the way, and I'm not certain why. And then none is to use the no true child strategy. I'm basically I want to return the last prediction. I mean, for my general rule of thumb, I'm going to take my best guess here and say I'm going to use the data that most likely falls into all of my paths. So let's go ahead and execute this. And I'm going to open the views simultaneously. There are two views that can be opened here. Okay, the first that's helpful is the actual decision tree view. And I'm going to make this a little bigger so you can see it outright. Now off on the right you can see this will allow us to zoom in and out and control the zoom control. So it's kind of an outline view of the decision tree. So the first thing it's doing is it's looking at the individual table, and the first column it's looking at is revenue from the client in the past 2 years. If it's less than 0.5, it's going to go down this path. If it's more than 0.5, it's going to go down this path. And then the table will tell you how many of these are wins and how many are losses, and the total number of records. So it's come up with a split here. Now I might take this one and continue to expand it out and say, then the next thing it's going to do is look at the total days identified through qualified. Less than 10.5 are going to fall down here. Greater than 10.5 are going to fall through here. And in each case I can see the percentages and the counts of the number of rows that are meeting at both the win and loss and total. And you see it's always, and I'll continue to expand this out and say the next part of this tree is the ratio of days qualified to total days. And less than 0.0099, you see how I'm getting down to a point where almost all of these are losses. And I'm going to keep expanding this one down, and then rule to market. And as you see each one, the next field it's testing is the route to market. And if it's equal to sales, I can expand that further. And so you get the idea that this is basically the view of the decision tree. This is the reason people like decision trees. They're viewable. You can understand them. And I can view it also in this format, which is also helpful. I find it sometimes easier to read from a human perspective. Revenue from the client in the past 2 years. See how many rows fell into each category. And see when I expand it, then I see the next test it did total days identified qualified. And then the ratio ID. Again, I can keep expanding this down until it gets to the final prediction. And both of these, like I said, are really useful views because, again, a human being can read them. I can turn this into a set of actual attributes. Okay, as the output of the decision tree that we've generated, there are some additional nodes in here we can make use of. The first would be, I'm going to take the decision tree to image and drag this up here. And I can execute this. If I show you the parameters, you can control the size and whether it should shrink down to fit or be truncated off. You can control all of that. But as it is, I'll execute and open the view, and of course my decision tree is so large that it's been truncated off. This isn't useful, but with smaller trees this would actually be something you could make use of. Also, the decision tree to rule set. I'm going to drag this node up and show you what this does. I can take this and I can basically use this to add to turn it into human readable format as actual execution code. So when I execute this, it's going to generate a PMML version of it and an actual rule set. The PMML is for, like I said, exporting to another tool that you want to run the model that Knime generated. But in this case, each one of the rules is expressed using Knime's language that feeds the rule engine and the rule engine splitter and so on. So it's basically Knime syntax. So if elapsed days is less than 15 and total days identified through closing is less than 49, and as I scroll all the way right, and it tells me that the output of that column is a loss. So this is all rule engine code. And then it tells me this is the number of records that actually follow through that node, and this is the number that the prediction is correct. And so again, this is just useful, particularly let's say you wanted to take this code and you wanted to run this in Python instead of Knime. Great, you use Knime to develop the tree, and now you go to Python to execute the actual code. And then one last node is under the JavaScript views. I'm going to drag the decision tree view out here and execute and open the view of the decision tree. And it's a slightly more a more intuitive use. You can expand things out to say, okay, show me the table, or I don't need to see the table. So it's an interactive view that allows you to do just what you saw out of the original, while showing you, it allows you to condense the table without quite as much information and still expand it as necessary. So it can be helpful when you want to do something interactively, especially if you are building a web portal, for example. Okay, now that I have my decision tree and we've examined it, I want to actually run the testing data set against that model to see how well it does. So I'm going to go ahead and double click on this, and if I want to highlight colors of wins and losses, you saw this is a 20,000 character data set. So if I really did want to be able to highlight this in a chart, I'm going to change that because there's 30,000, there's 23,000 I think coming in. Now it'll automatically append a column called prediction, and it'll give it then the name is prediction parenthesis the original column name. So you'll always be able to look at the two of them together. And I'm also going to append columns with the normalized class distribution. Basically, I want to see how likely was it to be a win or a loss. Looking at that probability just helps me understand the ones that got wrong. So when I execute this, I have the option of looking at the views themselves again. I can look at the decision tree as I had before, but I don't need to do that. I just want to look at the classified data. And I'm going to scroll all the way to the right here, and I'm going to drag my opportunity result. I want to put these two columns next to each other. So this is what the actual value was. This was a sales win, and my prediction for that column of the result is that it's going to be a win as well. And my probability, I was at 100%. I was certain that both of these were wins. This was a loss. I was certain it was a win based on when I'm looking at the probability. So it's kind of, again, useful information when I'm trying to decide what it's getting right and getting wrong. So this, of course, you can look at. There's 23,000 values here. There's no way for me to judge the quality of this model by scrolling through this data manually. So we're going to have to actually come up with a scoring mechanism to read it and determine how good is this model. Thankfully, the industry has a standard for this, and then I'm going to teach you that standard, and then we're going to go into how to implement that and how to process it through Knime. To determine how successful a decision tree model is at determining the predictor variable, we're going to use what's called a confusion matrix and several specific scores around the accuracy of the precision of this model. And so we're going to take a look at all of these in detail here. Let's consider the result here now of our win-loss example. All right, with my output in hand, I'm going to come into the node repository, and I'm going to look for the scorer node, and I'm going to drag that out here. And this is specifically built to handle, it compares two columns by their attribute value pairs and shows the confusion matrix. And additionally, it's going to show some extra information. So the first column I want to compare is the opportunity result. That's what we know happened. And the second column is the prediction for the opportunity result. And that's it. I'm just going to execute this. Okay. And there's going to be a confusion matrix and accuracy statistics. I'm going to open this up and execute it. Okay. This is the confusion matrix, where I can see it this way. I prefer to look at it this way. And we're going to look in the sample here. We're going to walk through exactly what each one of these means here in a second. And then the accuracy statistics. What this is going to tell me is in the row ID, I can see for the wins and losses and the overall, it's going to give me some really incredible information about the number of true positives, the number of false positives, true negatives, false negatives, recall, precision, sensitivity, and specificity. These are the really important measures. And then the accuracy of the overall model in terms of its prediction. So let's go ahead and let's look at start with the confusion matrix, and let's take a deep dive into exactly how that looks. So let's take a look at the confusion matrix to start with. On the left-hand side, under the row ID, these are the actual values in the data set. So meaning this was the historically accurate, which ones we won and which ones were a loss. And then across the top, the columns, those are the predicted values. And then what we see in between, or the data points, are how many times was it a win and we predicted a win. And when it was a win, but we predicted it would be a loss, and vice versa. In the loss row, how many was it a loss, but we predicted a win, and how many was it a loss and it matched as a loss. So in the confusion matrix, these row values actually have very specific names. When we look at a true positive is when the actual result was a win and we predicted a win. That is a true positive. A true negative would be when it was a loss and we predicted it would be a loss. So both of those are good things. Now, a false positive is where we predicted the actual result was a loss, but we predicted it would be a win. And then a false negative is we predicted it would be a loss and it actually was a win. Now, the meaning, of course, to each of those is really important and very specific to your use case. How bad is it, for example, if you were to say, if I predict we're going to lose this sale and we actually would have won it in reality, when I predicted we were going to lose it, did that mean I assigned my worst salespeople to it? You have to apply some meaning behind it. Each one of these and the implications of getting it wrong, especially the false positives and false negatives, are what's really going to drive how you implement your model in terms of a business process. Now, in that previous example, it was very easy because there were only two outcomes in the predictor variable, a win or a loss. In that type of example, the true positive, true negative, and false negative are just reversible. The use of the confusion matrix, you might think, hey, that seems like overkill, but it's easier to understand when the predictor variable has multiple values. So consider this following example using route to market as the predictor. Okay, so let's look at this example. In field sales, the row field sales, it was a field sale and I predicted it would be a field sale. That is a true positive. All the rest of them, if it was a field sale but I predicted any other value, that is a false negative. And the same holds true, so if I predicted field sale and it was not a field sale, then those are also going to be false positives, meaning my prediction was wrong. And then finally, all the rest of the values then are actually going to be true negatives. And so the confusion matrix gets a little easier to understand when you see it in terms of larger numbers of values. So with the confusion matrix set aside, let's take a look at some of the accuracy statistics that we're seeing available to us in the other output from our scorer node. The first one you'll see is recall, and this measures how good the model is at detecting positive events. Now, when you notice how, looking at the table on the right, I define, a positive is a win and a negative is a loss. For each prediction, I've got to define one of them as a positive and one of them as a negative, because the formulas get reversed when we come to recall. So when you look at recall, across the positive, it's going to be the true positive divided by the true positive plus the false negative. What it is, in essence, is what percentage did I get right, and when versus what percentage I got wrong. And the precision, looking down, is just the same thing. With the positive column, it's what's the true positive divided by the true positive plus the false positive. Now, when we deal with the negative columns, you can see that I've flipped it. So instead, now the negative column, the recall value is going to be true negative divided by true negative plus false positive. So in essence, the formula has turned. That's why I've color-coded the box to make it read this way. So these are the first two statistics. Recall measures how good the model is at detecting the events, and precision measures how good the model is at assigning positive events to a positive class. That's usually the most important piece of information to somebody asking you to build a model. Now, alternatively, recall and precision can be reported as a single measure by combining them together. And the example that Knime uses, they call the F measure here, which is the harmonic mean of recall and precision. So, in other words, the F measure is computed as 2 times recall times precision divided by recall plus precision. Continuing on, sensitivity is the measurement of the ability of the model to recognize one class correctly. So the sensitivity would depend upon the row ID. How well did I identify win versus loss? The formula actually is exactly reversed. It's for sensitivity for the winning column, it's true positives divided by true positives plus false negatives. And specificity is the ability to recognize who's not in the class. And that's going to be, again, the true negatives divided by the true negatives plus the false positives. And again, that's when I'm looking at sensitivity and specificity on the win column, or on the win row. On the loss row, you would revert those formulas. Now, the overall accuracy measures the collective ability to determine who is and who is not in a class. And therefore, the accuracy is going to be equal to true positives plus true negatives divided by true positives and true negatives plus false positives and false negatives. So again, I find that to be not all that useful a measure because I'm usually not interested in the negative result, only the positive. Finally, Cohen's kappa is presented to you, and it represents similar to a correlation coefficient in that it ranges from -1 to +1. And it represents the amount of agreement that you find between the raters. Cohen himself actually suggested that kappa be interpreted as values less than 0 indicating no agreement, and values of 0 to up to 0.2 as having none or slight, and 0.2 to 0.4 is fair, 0.4 to 0.6 moderate, 0.6 to 0.8 is substantial, and 0.8 to 1 is almost perfect agreement. And that's kind of his view of it. So with the confusion matrix set aside, let's take a look at some of the accuracy statistics that we're seeing available to us in the other output from our scorer node. The first one you'll see is recall, and this measures how good the model is at detecting positive events. Now, when you notice how looking on the table on the right, I define, a positive is a win and a negative is a loss. For each prediction, I've got to define one of them as a positive and one of them as a negative, because the formulas get reversed when we come to recall. So when you look at recall, across the positive, it's going to be the true positive divided by the true positive plus the false negative. What it is, in essence, is what percentage did I get right, and when versus what percentage I got wrong. And the precision looking down is just the same thing. With the positive column, it's what's the true positive divided by the true positive plus the false positive. Now, when we deal with the negative columns, you can see that I've flipped it. So instead, now the negative column, the recall value is going to be true negative divided by true negative plus false positive. So in essence, the formula has turned. That's why I've color-coded the box to make it read this way. So these are the first two statistics. Recall measures how good the model is at detecting the events, and precision measures how good the model is at assigning positive events to a positive class. That's usually the most important piece of information to somebody asking you to build a model. So if I can come back to my scorer and look at my sales win-loss model, and I'm going to look at my accuracy statistics. What I'm interested in is wins. If I'm looking at my sales data, I'm most interested right now in who are the sales opportunities I'm most likely to win. I only win true positives, 3,300 records, 16,000 are not going to be, they're going to be losses. So what I want to know is, because I want to focus some of my efforts and resources on the clients I'm most likely to win. So it's this win column right here that I'm interested in terms of this model. And in this case, sensitivity. I'm able to predict which sales opportunities I'm going to win 64% of the time. I'm able to predict who's going to be a loss 90% of the time. It's such a better score because, of course, most of our sales are losses anyway. So just even random chance, if you guessed without any model at all, you'd still be right the bulk of the time. So this, in terms of sensitivity. Now, who's not going to be a sales win? Of course, since there's only two outcomes, these are reversed. These would of course change when we use the example of the field sales example that I just went through. So the accuracy, when you look at this, it tends to get easily confused. People will say, look, this model I just built is 84% accurate in terms of predicting sales wins and losses. Well, yes, that's true, but it's because it's so heavily weighted on the loss. The value I'm really interested in this particular model is sensitivity. I'm only going to win this 64% of the time. So don't get wrapped up in the accuracy number. That's not always going to be the best number to judge the quality of your model. One really good way of looking at this is with an ROC curve, which is the Receiver Operating Characteristics, ROC. It's a graphical plot, and it illustrates the performance of a binary classifier like a win-loss as it discriminates the threshold is varied. The curve is created by plotting the true positive rate, which is our sensitivity, against the false positive rate, which is 100 minus specificity. And it does that at various threshold settings. And let's look at this graphically to show how you can see this. All right, so let's come back to our model here again. And in the repository node, let's search for the ROC curve. And let's put this out onto our workflow. And I'll connect them up. And this is very simple to piece together. So I'll double click to get my configuration. And the class column is actually the opportunity result. That's the one we're trying to predict. And the values for it, am I trying to predict the wins or the losses? In my case, I'm concerned with the wins. It's the ones that I win that I'm interested in trying to find a value for. And I want to plot this against my opportunity results. I want to see the actual results of the one. And I'm going to click OK, and I'm going to execute and open this view. And let's look at the ROC curve. What this is it's measuring the area under the curve. And the area under the curve in this case is 0.776. So I've got about a little over 3/4 of the area under the curve is covered, which means I'm doing pretty well in terms of my ability to predict who's going to be a win. And what you can see is the number of true positives up here across the number of false positives. But my total area under the curve, like I said, at 0.76 is actually a really good result. Just for fun, I'm sorry, I should have looked at the curve. Last thing I should have explained to you, the line here across the center, that represents random chance. Meaning, if you just like flipped a coin and said, am I going to win or lose this? You'd see some on both sides of the curve. We're doing much better than random chance with this model. Let me show you an example of why that would be different. If instead of looking at the wins, if I were to look for the losses, and if I plotted the wins against the losses, it'll all be below the line. As I show the area under the curve, well, I'd be much better off just going with random chance if I was trying to predict wins and actually plot it against the loss. But let's look one more time. Let's change this once last time and actually look for a loss. And I'm plotting the opportunity, so I want to see how well I do at predicting a loss. We had 77% under the curve at predicting a win, and I get 78% slightly better at predicting a loss. But again, does that matter to me? Am I interested in predicting which sales opportunities I'm going to lose? I'm more interested in predicting which sales opportunities I'm going to win. And I know I'm harping on that point, but it's a particularly important point because when you develop models, people focus in on the model accuracy, and that's just a huge mistake. You need to think about the business use case that you're trying to solve, because it's usually just one specific value in the predictive column that you're interested in taking action upon. Finally, I'd like to introduce you to the concept of lift. A lift chart graphically represents the improvement that a data mining model provides when compared against random guessing. And it measures that change in terms of a lift score. Now, with a lift chart, it's actually kind of neat because you can compare the accuracy of predictions from multiple different models that have the same predictive attribute. And so you can also use it to assess the accuracy of prediction either from a single outcome or from all outcomes of a specified variable. So to add a lift chart to my model, I'm going to go into the node repository. I'm just going to search the word lift, and I'll add the JavaScript view for lift chart and connect that up to the output of my model. And of course, what I'm trying to do is the opportunity result and the probability columns that were generated. I'm interested in the probability of a win, and I'm labeling this wins, and I'm just doing increments of 10%. You can do this as you need to. I'm going to execute and open the view here now and look at my lift chart. And the first you'll see is the green line represents random guessing, random chance. So meaning if I just guessed wins or losses, that's what it's going to be. what it tells me right now is for about the first just under 35% of the incoming data set, I'm able to guess with great accuracy the people who are going to be a win. And I fall less than average below it, but the cumulative line, blue, is the sum of all of mine. And therefore, when I look at the cumulative wins and losses, even across the percentage of the group, I'm always above. So it means my model is better than random guessing, at least. So meaning if I was to ask a senior executive, am I going to win this contract or not, I'd take this model over a random guess from a leader any day of the week. So this still provides me what I want to see. Now, lastly, just for fun, I wanted to show a comparison. In our first decision tree, I used the quality measure of Gini, and in a second one, I created and ran the exact same two data sets through, but this time I switched it to a C45 tree inducer instead. And I wanted to compare the results of the two of them. So I'm going to look at the accuracy statistics of the first one right here, and I'm going to overlay the accuracy of the second model here so that I can see them together. And you can actually see the decision trees have produced slightly different versions. The C4.5 has produced a little bit better ability to predict who's going to be a win. Now, it doesn't do as good at predicting who's going to be a loss. Again, I'm thinking I don't care about my ability to predict a loss. I care about the ability to predict a win. So as I look at these two models, I'm probably more likely to go down this route. And of course, some of the other parameters, once I settle in on models, some of the other parameters you can turn around and continue to play with are to say, instead of reduced error pruning, I want to go with MDL pruning. I want to change the minimum number of records per node. You could use the same methods that we did with dimensional reduction. You could sit and tweak some of these parameters to find some optimal settings. If the level of discrimination in your model is so important, then it's worth taking the time to go through that exercise to get it right. There are a lot of advantages to decision trees. The most important one to me is that they are self-explanatory. Even the non-data science professional can read them and understand what the model says and means. They can handle nominal and numeric data. They're rich enough that they can represent any discrete value classifier. They handle data sets with lots of errors, and they handle data sets with lots of missing values. And these are all big pluses, because that's kind of the real world. The disadvantages for trees are that most of the algorithms require that the target attribute have only discrete values. The decision tree uses this divide and conquer approach, which works really well if you have a few highly relevant attributes that exist. But they're also overly sensitive to overfitting. Because the training data set, it's so easy for them to attach onto irrelevant attributes and noise that other methods aren't quite as susceptible to. So throughout the course of these sections, we're going to keep showing the result comparisons. We're going to keep running the same data set through each result. And you're going to see the changes in sensitivity and model accuracy. And it's important to remember this. There is no right model. The numbers change with the data. In this case, for example, it's appearing that the decision tree cart format inducer is just a little bit more accurate than the C4.5. But in terms of sensitivity, which is the important part to me, I'm looking still and saying, when I focus in on that number 649 versus 641, then it looks like C45 is just a little bit more accurate. And of course, that was without any tweaking of pruning and other methods like that. But we're going to stop with that for now, and as we go through each chapter and add another mechanism, we'll keep reflecting the results. But the important thing, please remember, your data, the contents of it, the distribution, null values, all make a difference. And so you can't look and say, I'm always going to use C4-5 decision tree as my result, because sometimes it will outperform an ensemble method, and there's always opportunities. There's no best model. You have to go with the one that works, so you're going to have to try them all. So, quick chapter summary. Decision tree is a set of rules applied to a group of independent variables to predict the outcome of a dependent variable. The principal output is the confusion matrix, which shows us true positives and false positives, and true negatives and false negatives. The accuracy statistics for measuring it, while accuracy is important, sensitivity and specificity are more important. Sensitivity being the ability to detect who is in a class, and specificity is the ability to detect who's not in a class. That completes this chapter of the class. Feel free to move on to the next chapter.